All right, we're back for day 11. Welcome back, welcome back. Today we're going to Pluto, apparently. Plutonian pebbles. Those like fruity pebbles? Okay, stones arranged in a straight line. Each stone has a number. Every time you blink, the stones change. Sometimes the number engraved on a stone changes. Other times the stone might split in two, causing all... Okay, so there's some rule set here. Okay, so every time we blink, every frame, we'll call it, everything simultaneously changes all at once. So the first applicable rule in this list, if it has a 0, it's a 1. If it's even, it's replaced by 2 stones. The left half of the digits are engraved on the left stone. Right half are engraved on the right stone. So the easy way to do this is to stringify it, I guess, or keep it as a string in the first place and then split it. But we could also do this in other ways, like multiplying by, 1,000 and whatnot. If none of the rules apply, the stone is replaced by a new stone. The old stone's number multiplied by 2024. Order is preserved, and they stay perfectly on their straight line. How will the stones evolve if you keep blinking at them? If you have 5 stones... Oh, okay, so we're going to have to, keep track of where these are. Got it. I guess technically they are always in the same places, so I feel like I want to make that a tree, but there's probably a faster way to do it as well. So 0 becomes 1, 1 becomes 2024, third becomes 1 and 0, 2 stones. The fourth stone is 9 and 9. Fifth stone doesn't match, so is multiplied by 2024, it looks like. So this is the next set of stones. This seems iterator worthy. We can kind of just keep producing this forward, flatten it out, keep producing this forward, flatten it out, keep producing this forward. So you have 22 stones after blinking 25 times. You have 55, 312. So just create day 11. I feel like this is going to be really easily done, or rather not easily done, but I think the approach that sits in my head immediately is iterators, which if you've seen my other videos for Advent of Code may not come as a surprise to you. Here's a longer example. So here's our first 125 and 17. I guess we have both tests too. Do we have the 25 number? No, we only have 0 to 1 there. So I think unless we run into a problem, I'm going to leave just the one test. We do have the opportunity to write multiple though. The puzzle input is not very long, but I am interested in some of these numbers. I'm going to assume that U64s are enough. So input needs to be in split ASCII white space is fine for us. And this technically gives us our first iterator. I think in this case, I want to parse everything. So we'll parse that into a U64. Assume that always works. So instead of unwrap here, expect numbers to be valid in AOC. And if we debug it.collect, I'll throw this into a vec for the moment. This will be a vec of U64s effectively. Day 11 part 1, this should run. And we end up with 125 and 17, which is what we should end up with. In an iterator, we use split ASCII white space because we know Advent of Code only uses ASCII characters. There's also split white space, so not a big difference between the two. ASCII just came up first in the list. We map over that, we parse the numbers, and we're leaving it in an iterator for the moment. I don't know if I'm going to leave it forever. So we currently don't actually care about any of the intermediaries, but knowing the intermediaries would help debugging. So we've used scan before, which starts with some state and then continues. We, as far as I can think of, don't need any state that isn't held in the iterators. So I'm basically just writing the first step here because we need to do this a bunch of times. So this should give us step 1 or 0 to 1, basically. So we get some number and the rules say these things, or not that, that's not the rules. This is the rule set. I'm going to grab these rules and I'm going to drop them in here as comments. And we're going to turn on word wrap for this one. Okay, if 0, so I guess we match num, right? Match num, except that we only test for one value. So match isn't as useful, right? Because we would have 0. Let's debug 0 here for kicks. And let's get a panic in here for anything else. This is not the way to write a guard. I've reversed it. N if this then. So we can write guards like this. which is nice. And this is warning us basically that we're not using this. So let's see. We're just it.mapping here. So let's set it to it.map maybe. I think the types aren't going to match up if we do that. So we can do last here. Again, I'm just working through this for the first time. We'll clean it up a little bit later. So this is, if we have a 0, then we get a 0. If, I feel like we aren't getting any debugs on the left-hand side here. Maybe that's because let's debug num here. Is this running? It's not running. I'm collecting here. Okay, I think we were getting an optimization where this always returned unit, so it wasn't doing anything. So we've got 0. This would need to be 1. I think we're going to put this in an array because other things are going to be arrays. If the stone has an even number, it's replaced by 2 stones. So let's say this is like 2, 2 for the moment. And the right half, our right stone, left half, left stone, yep. And if nothing else applies, a stone is replaced by a new stone, which is multiplied. So n times 2024 would be our fall through case. And on the end of this, we can into iter, I think. No, we have to into iter inside. So instead of dealing with these potentially being different types because these arrays have their sizes built into them because I'm kind of hard coding it at the moment, I'm just going to throw them into Vex and clean it up later because we haven't even solved the problem yet, so I'm not really worried about it. So this gives us these two numbers. This is not the right. 25, 3000, 1, and 7. 25, 3000, and... oh, if num... let's do n here. If the stone is engraved with a number that has an even number of digits, that is different. I thought it was even, not even number of digits. So even, I wonder if there's a function to return the number of digits. So I think we can actually use checked ilog here. And that does seem to work. I can't say that I've used checked ilog 10 much before. So I'm honestly not 100% that this is everything that we need it to be. But if we click on the documentation, this will be 5 checked ilog base 5. So let's debug this instead of, right? So theoretically, this could be 10, 15, 20, and these would be 1, 2, 3. And if we base 10 that and bump these up a little bit, then we get 1 digit is 1, 2 digits is, 1 digit is 0, 2 digits is 1, 3 digits is 2, 4 digits is 3, etc. So I think we're good. So we check to see if that is mod 2 equals 0, if it's even, because we need to basically check the number of digits here, we need to add 1. So like this is 1 digit, so it's 0 plus 1, so on and so forth. So we end up with these two things. If this is true, then what we actually need to do here is, right, so this is num digits then, and we can split at num digits over 2, .iter.map. I don't actually remember what split at gives us. It's probably a vec. So we probably get each individual here. So we can parse that back into a U64. This looks like it is not iter able. So we might need to actually into iter. N2 string split at. This num digits is a U32 in this scenario, which easily fits into a U size. Iter, oh, we get a tuple out of this. We don't get a thing to iter over, so we can get left, right, and we basically want this with left here and right here. So we're doing a lot of like toString and parsing. Oh, a temporary value is freed while still in use. So n.toString.split at, we just need to give it somewhere to store that value while it's still used. So if we expand this out, the issue is temporary value dropped while borrowed. N.toString creates some data, and then it's freed at the end of the line or dropped at the end of the line. But the reference that's created through split at, this left string slice or this left value here is a reference to that string we created with n.toString. So this string value gets dropped at the end of that sequence, but left is still trying to reference it, and we try to use left later. And this is technically split at on slices, but this gives us shared references to the original slice. So we can kind of confirm that and do let n string equals that. So now n string stores this capital S string. I can prove that to you by showing you the inlay hints. This split at then keeps these two string slices for us with references into this string, which is now hanging around to the end of the block. And then we have the output that we expect here. So this isn't the fastest way to do like digit to string split in half kind of thing. I think if I remember correctly, multiplication would be faster. So we could do like a fold over the digits and multiply them or something like that. But this will work for now. I know it works, so I'm just going to move forward with that. And we can always make it faster later. So we actually need to run this multiple times. I feel like this is a fairly decent use case for something like successors. In my head, I would like to keep everything around in iterators forever, but I know it's going to be easier to, say, collect this into a vec, and we still have part 2 to do. So I'm going to start with that approach. I'm going to say successors is some nums here. We're going to basically take this that we just did, minus these comments, we don't need them anymore, and pull this in up here. This is going to be nums. We're going to iterate over nums, flat mapping, collecting. And I think this just goes forever. So I don't think this is ever really going to end. So we'll call this next nums. This will be a vec of U64s because we've flattened it. And we'll return some next nums. And checked ilog is giving us an issue for a moment. Can't call checked ilog on an ambiguous numeric type. Our ambiguous numeric type is ambiguous because... Oh, because I didn't specify the vec up here. So this is a vec of U64s. Now we know that. Last doesn't exist, but successors does. So we can do all iterations like this. And what I want to do is all iterations dot, let's say take 5 collect. And we'll just debug this for the moment. We need to collect this into a vec. And then we end up with all of the iterations here on the left. So the reason I kept these all around is so that we can debug this like this, because I think this is really nice. So let's pull in all of these, right? 1, 0, 1, I guess 1, 2, 3, 4, 5, 6, 7. So we should do 7 here. And what we seem to get out of it is the right answer, the right answer, the right answer, 1, 20, 24. Yep, that looks good. That looks good. And briefly scanning the larger lists because all of the other ones have been correct. That also looks good. So I think we're good here. I forgot what we actually needed to do. After blinking 6 times, you would have 22 stones. After blinking 25, you would have that many stones. So we need to skip a number here. So let's say skip 5.next.count .unwrap because it has to exist. And oh, that's not what that issue is. That issue is going to come up, I think. But, oh, let's just do .length here, actually, because we're going to get that vec back. And this is going to be an option. So we'll unwrap that. And what we end up with is 13 here. So let's see what we get if we skip 6, 22 here. So after blinking 6 times, that's the number we need to take. And then the next one has the amount that we need. So this should be 25. We'll call this the result. We'll do okay result.toString because I have strings as the return types of all these functions for me. That, oh, right. And then Clippy is reminding me that I can do nth. So instead of skip 25, we can do nth 25. And then I don't think we need to do next. But for that change, as it said, we do need to make that mutable. And let's make sure that our test is actually passing by failing it like that. Let's get rid of this debug. Again, we're doing extra allocation up here with these vecs, but not too concerned about it at the moment. We can always optimize after we get the right answer. So day 11 bin part 1 gives us an answer. Is it the right answer? It is the right answer. Huzzah! And then we just need to do it for 75 times. I have an inkling that I would want to run this with the release mode. So I think we're going to do the 75 there and just run it and see what happens. I don't know if that's going to end because 75 seems very large, but we will run it while we're doing the explanation and see if it finishes. And if it does finish, then we're good. And if it doesn't finish, then we need to figure out another solution and figure out what's preventing it from finishing and how do we skip some of that processing. So in the meantime, recap on part one. We start with a list of numbers separated by white space. So our parser today is just split ASCII white space, parse into numbers, and collect as a vec of U64s. That gives us a vec of U64s here that we can work with. We then create this iterator that starts off with that vec, iterates over that vec, applies the set of rules that we need to apply, and collects, then returns that next sort of iterator as the next value. So standard iter successors will just keep producing this value for us as long as we keep hitting next on that iterator, which is really nice. It worked out really well for part one. And the way that we kind of got around having to deal with any type issues here is we returned a vec for each of these. That isn't amazing in that sense, right? Like this is a vec of 1, this is a vec of 2, this is a vec of 1. So we probably don't need to be creating so many vecs, but it makes it a little bit easier to write the algorithm in the first place, at which point we can then optimize. So our rule set uses match. So we flat map over this because we know we're going to create this vec and we want to destroy that extra layer. So we match on num. For 0, we just return 1. For n, we do a checked ilog 10, which we add 1 to, which gives us the number of digits, which we can mod by 2 to see if it's even. If it is even, then we're going to get that number of digits. We're going to turn that into a string, split that string, and return our 2 numbers. Now, this is probably one of the areas where we should do something different. I truly have no idea how long the program is going to run for 75 iterations. I didn't check at all. We ran right into the part one explanation here. And in general, I'm very happy with the code flow of successors, the solution that we went with here. It can definitely get cleaned up. It can definitely be more performant. So that is part one. And then part two is just doing it at scale, right? So I don't know really even how fast 25 items is, but we might want to turn this into a function that accepts a number and just see how long it's taking, so that then when we do performance work on this, we can actually benchmark against 1, 10, 25, and so on. So I'm somewhat curious about how long that's going to take to run. And in the meantime, I think we can get in on some benchmarking. So let's change this back to be blinks, I guess. And process will then take a blinks argument as a U64. I guess it doesn't really matter. We don't do more than 75, so it could be a U8. But let's save that. And then that should break, for example, our benchmarking. We're not actually going to end up using this part 2 file today, so I think I will delete it. Delete that, delete this. And then Devon has this really nice stuff where you can use consts, for example, to set up a variety of benchmarks that will compare against each other. So in this case, they're doing 1,000, 2,000, 3,000 and checking the benchmarks for that. So I think we will set this up specifically, and we should do what, like 1, 10, 25, 40. I don't know how long 40 is going to actually take. I feel like I just messed up my syntax too. Bench, parens, equals. Oh, I added an extra array thing there. No, they're just out of order. And we should be able to slot n in here, give those a little bit more space to breathe, and run the benchmark. Well, I messed something up. Oh, right, because our bin also needs to accept that number. I think we can do env args, which is going to need to come in, right? Standard env args, and then I think we need nth, we'll say 1, skip the program name, and then this will be, I guess args is no longer going to be the arguments in total. This will be the number, and this will be num parse U64 unwrap, or rather expect, because this is user input. So expect number to be parsable, save that. Let's do cargo run part 1, 1, I guess, and make sure that this works. Oh, we don't need usize, we need, or rather we do need usize, and this is process 25, I think, for the test, if I remember correctly. No, 5513 is 25, yeah. So we should be able to do 1 here. Oh, args, args can't handle that. Bin part 1. Part 2, we will also delete. We don't need part 2, we only need part 1. So if we env args nth 1, we get an option of string, which means that we can expect or return this. It doesn't matter because our program's going to crash anyway, or our program's going to stop anyway. So we could use one of these handy functions like okay or blinks argument, not parsable. It is notable that my system ran out of application memory just now. So I'm going to check my recording software and make sure it's still running. It does look like it's still running, which is great. But this was because of the running program. So we're just allocating too much effectively for this to be either efficient or run in any useful amount of space and time, which is, I'm going to say it's fine, but it's only fine in the sense that like not really a problem. It just won't finish actually, which I was actually very interested in seeing if this was going to finish or not. So let's do cargo run 1. We have Miet in here, so I'm just gonna use Miet to write this error message. Miet macro, which I didn't bring into scope. So a little bit of extra work in setup today to get these benchmarks to run. Let's see. So 1 is 11, 2 is 16, 0 is 8. Does that sound right? That doesn't sound right. So let's test day 11. Day 11's test looks good. So result all iterations, blinks as usize, unwrap.length. Feels weird that we're getting these numbers. Let me pull this out for a second. And we're going to debug T here with a shared reference because that is what we have to do. So, oh, right, because the actual run is not the same as the test. That's all it was. Okay, never mind. This is not an issue. This is just different input than what I was thinking of, right? So we can do a number of steps here. 6 seems to run, 10 seems to run, 20 runs, 25 probably also runs. Does 40 run? Not really enough for a benchmark, I don't think. So let's try 30. 30 runs, 34 runs and takes a while, and 32 also. So we're not going to do 40 here. 40 is a little too high. And we'll replace that with like 32, which is a fairly reasonable number from that perspective. That's interesting. Malloc stack logging, can't turn off Malloc stack logging because it was not enabled. I don't know if you've ever seen this before, but I have never seen that before. So let's make this a U64 here for the benchmark because I think that's all that was. And we can start to see some of the output here. 32 should take a second. I think that 25 is probably enough for us to realize that there are performance wins. But I am interested in seeing something a little bit higher because we do need to not just get to 32, but get to, 75 or whatever. So we end up with about 470 milliseconds on day 11. So I'm going to take this and save it. And I think wipe out 32 from this benchmark because we don't really need it to see that we got an improvement, but I was interested for later. So I'm going to drop that into my benchmarks file here so that I don't forget that these are the numbers that we originally ended up with. And now we actually have something worth benchmarking. I wish I could get individual columns output here. So now we're set up. And I think that there are probably 2 different places that I can think of that are really affecting our runtime. And that is maybe the allocation of these vecs and also the number processing here. I'm also skeptical that we actually need U64s. We could potentially get away with U32s. I don't know that for sure though. So that's going to be something I do later, if at all, because it's also a fairly straightforward change. So we already have the number of digits here. So after a little bit of experimenting on Rust Playground, I took a number, I got the num digits, which we're already going to have. I took 10 to the power and I did modulo to get the remainder and division to get the front side. And I kind of thought there was like a div rem operation in the standard library that would do both of those at the same time. But I think if we're going to try to do that, we would need to go out to num traits. And I think that this is where our Rust Playground adventure ends, because I don't think num traits is actually on there. Oh, it is actually. It did work. It just didn't autocomplete for some reason. So with div rem Euclid from num traits, we can do that and then get left and right here. So this is going to be the line of code that we want here. And we can get rid of all this parsing and toStringifying. And we do need to install num traits, which I'll do cargo add num traits package day 11. Rust Analyzer catching up. We need to bring that in. And then I think that works. Let's run our test. Our test runs. Let's run our bench for kicks. And our previous benchmarks, our current are 733 and 15. And our previous were almost 1,000, 50, and 24. So we dropped 10 milliseconds off our time by switching from parse and toString to doing a mathematical div and rem modulo, which is wonderful. That's a great improvement. So with that improvement, I'm also curious about what our higher bench is for 32. It still looks like it takes a decent amount of time. So almost certainly not the only thing we need to do. But we were looking at 470 milliseconds for 32 before, and we're down to 310. So we dropped 160 milliseconds off our runtime there, which is wonderful. So if we run 32, it just pops out for us. If we run 35, takes a little bit longer. If we run 40, which was taking way too long before, I think that we don't have enough performance to really benchmark that. That looks like it took 9 seconds. So we're moving up and we're getting things to run faster, but we're not getting them to run in, I think, enough time to do 75. So if we want to switch to arrays here, I think we theoretically can. We can't do it in the match though, because this is an array of 2 values. Or rather, this is an array of 1 value, and this is an array of 2 values. So one really interesting potential way to solve this, let's do cargo add here, is a crate called either. Either basically implements result, but where left and right are not success and failure, but just 2 different types. Because we want to return an array of one size or an array of another size, we can then wrap it in the left or the right branch of this. We could write this by ourselves, but I just wanted to point out that this exists, and not just as a small side implementation, but a fully fleshed out type and crate. And actually, if we do it this way, then we have left and right. And interestingly, if we do that, we do either left and either right, and we do into iter here, then this all actually does work out as long as the iterators are the same type. And even doing that small change turned this into a benchmark that is running in 370 nanoseconds, 10 microseconds, and 5 milliseconds. So from our original benchmarks, we're down from 900, down from 40, down from 25, and down from 470. So our numbers are getting better and better and better. Our first change was to, instead of toString and parsing, use a little bit of math to get the split of the numbers. The second was just removing those vecs and turning them into arrays. And let's take a look at how long 40 takes now. I think it took 9 seconds before. It now takes 3. But we're still kind of blocked like below 50-ish, right? 50 is taking quite a while. 40 took 3 seconds. I'm not exactly sure what the scaling on this is, but I'm not throwing 40 into the benchmark for a 3-second benchmark. And you can see us go from nanoseconds to microseconds to milliseconds to seconds, right? I think we have to write a completely new solution for part 2. So let's write part 2, and then I will kind of fix part 1 again. And then we'll write this to be for part 2, copy a bunch of this in. This is basically the same thing. The benchmarks are going to work the same way. The function is going to work the same way. I think our logic for the cache hit and the processing, or at least the processing, right? This whole match here, so down to the yellow. This isn't the right name for this function, but it's like process iter and contains all of our logic here, right? This is the, if we have to do processing, this is the function we call. Now the question is, what are we storing here? How are we keying into this? If we have one of these numbers, we will be able to get down the tree. So after thinking about this for a little bit, the very high number count of values that we have hits the cache billions of times. We only need to keep the numbers for how many stones there are at the end. So I think for every iteration, assuming that we're hitting the cache that many times, we could reduce it down into the number of stones that we have for any given number for the cached value. And then I think actually the processing might not need to be cached. So like we don't do caching for the processing at the moment anyway. And I'm just going to leave that there for a second. So we don't do it for that. We do it for, right, this is a key to the number of them that we have. So stone number and stone count, right? And then we don't need anything fancy here. right? For I in blinks, because we don't need each of the actual outputs, which is kind of silly. Like the idea that we wouldn't actually need the values, but we're going to count them all anyway. Then we're not doing this caching thing. So I can grab this and stick it back here without really caring all that much, because we'll just do the processing. It won't matter, not compared to all the other stuff. So next nums is this. And this is not for I in blinks. This is 0 dot dot blinks, probably dot dot equals blinks. We get rid of all of that. And what number do we actually need? The number of stones. So that'll be adding up the values of the cache after we're done. So cache values, sum them, turn that into a string. Cache is storing the stone count for every stone type. Every stone type turns into something else moving forward. Are these the right values then? Right? Because we are no longer producing the results. I guess like this isn't really a cache anymore, but we'll take nums, which is a vec of U64s, right? And I guess we can kick off our hash map like that, right? I actually don't know if our input works like that, though. Are there any duplicates? There are no duplicates, but I don't think I want to rely on that. So, right, for num and nums, cache dot entry num or insert 1. So end modify v plus equals 1 or insert. This is cache, not the cache. This does not need to be returned from anything. This needs to be dereferenced. So we get nums as a vec. We create our cache. We insert into that cache with our starting numbers. This should be the starting numbers. The order actually doesn't matter, even though the problem says their order is preserved. But like their order being preserved literally does not matter at all. So love to be misled by the problem description. So for I in 0 dot dot equals blinks, we take this cache and we have to process every number in the cache and then create a new cache, I think. I think that's fine. There's 4,000 numbers in the cache, so I'm actually not very concerned about this. So we could do like new cache here, and our logic is basically going to be the same. So new cache is cache.iter, right? But we don't actually even need this. We can just do for item in cache. We don't actually need to flat map this or anything fancy like that because we're just not going to be doing anything with it. We don't want the actual results. We do need that match in here though. So if we match on, I guess we can call this num. This is ID and, or rather num and count, we'll call them. So this has to be values of 1, right? So we'll get the entry for 1 in the new cache so that we're not reusing old values. And this can be into iter because we're just totally consuming it. So entry 1 and modify. If there's a value there, then we take the count and we add the count. Otherwise, we insert the count. Then if we have the checked log thing that we need to do, then we have something on the left and something on the right. These are our new numbers. So in the same way, we need to do left here and we need to do right. And then here we need to do n times 2024. And that should be it as long as we reset this cache at the end. So match num, new cache equals, or cache equals new cache, I think it is. Cache equals new cache. And then this is cache.values at the end. Let's debug this cache. New cache here has an issue for some reason. Borrow after move. I guess we move it in here, don't we? So let's do this. Let's look at what the compiler is telling us. New cache is borrowed after move. It's moved here and it is borrowed. It's used in the next iteration of the loop, it's saying. I feel like that should be fine. New cache is a hash map. This reinitialization might get skipped. We don't really want it to reinitialize. We don't return from anything. I guess this just keeps doing cache, doesn't it? Cache into iter. How would new cache get skipped? This reinitialization might get skipped. Oh, yeah. But that's fine, I think. And then cache, this reinitialization might get skipped. Why would it get skipped? If this is not an iterator, if there's no values, it would get skipped. Right, we don't actually want this. We want this. Yeah, it was inside of 1. I didn't realize it was inside of here. This is I. I guess we can keep I around, but it doesn't really matter, right? If we debug I, then we'll see what round we're on of blinks. So if we run the part 2 test, we do get a passing test. I was not prepared for that to actually pass, but we did write our logic already. So it is actually passing. So we could bench. I want to get rid of these debugs before we bench. One of the nice things about using, tracing and whatever. So let's debug that. Oh, I still have another debug in here. Not in part 2 though. Oop, I accidentally pasted something. Just very much not flowing smoothly today. So this is part 1, 110, 25, 32. I think we only really care about the difference between them. I'm going to remove the cache for part 1 because it's actually faster to remove it. But I think that if we have a successful part 2, it would also run faster for part 1. Yeah. Okay. There we go. We've got 1 microsecond, 23, 217, 500. Yeah. So I guess let's bump this up to cargo run release 50. See if that runs. Oh, that's part 1. Hang on. I need to not be running the slow solution for the higher numbers. I don't have the part 2 bin because I deleted it because I'm a genius. Input 2, process, run this. It runs basically instantly. 60, 70, 75. Let's run 25 and make sure it's so I guess we can bench this at all of the numbers, right? 50, 60, 70, I guess 75 because it's relevant and special because it's one of the answers to the problems. And then we can kind of do I guess we did 32 there. So we'll do 32 here and then we'll go up by those until the top. So this is our 75 answer, right? Hopefully that's the right one. Let's run our bench and I'll go over here and check to see if this is in fact answer is too high. It's probably -1. So part 2 ... equals blinks. I don't know why the test is passing then. Oh, because I did the -1 down here. I did the -1 here and I didn't put it into, okay, that makes sense. So this is the actual answer because now we're actually doing the -1. Oh, you gave an answer too recently. You make one mistake and it times you out forever. Okay, I'm pretty confident this is the answer though. We need to do 0 ... blinks because 0 is actually a step. So we don't include that other one. I guess I'll cargo bench this while I'm waiting my 20 seconds to resubmit. I'm going to sit here and use the benchmarks as a timer before I can resubmit. 7 milliseconds. Okay. Submit. We got the right answer. 11. Done. So for part 1, I'm going to remove the caching that we were talking about entirely. The caching does not help part 1 in the way that we were doing it. We did have to actually redo our implementation there for that to even work, because the thing we were doing in part 1 when we tried to do the caching was caching individual values, which is not useful. So if we do that and we do our cargo bench, then these should run in about half the time, which they do. So they're not particularly fast. Like 32 for part 1 takes a little bit of time, 98 milliseconds. And our total runtime for 75 for part 2 is 7 milliseconds. So big difference is that part 1 generates all of the values and returns them to you so that you can use them. But that is slower than cutting out all of the computation and just counting stuff. So I think I probably would have left this as successors if I didn't think the original cache was going to work. I'm still happy with things like either, things like this ilog10. I think this ilog10 thing actually does come back up. And then we don't use either at all in part 2 because we're not actually doing, we're not actually getting the results, which always feels strange. But so for part 2, our goal is the exact same, but this is supposed to be 75. Is there an answer for what 75 is? No, the test is the same. So we'll leave the test. So we get these two numbers. We have some fairly simple rules to apply. If it's 0, then we turn the stone into a 1. If it is anything other than a rule that we have, we multiply by 2024. And if it is an even number of digits, then We do the div rem Euclid and split it in half for, half the digits on each side. The big insight for today is that you don't actually have to do any of the processing individually for any of the numbers, because they all happen to be set up correctly to be a small number of varieties of stones, we'll call them. Like there's a small number of stone numbers. So if we store the count with those stone numbers, then we don't have to do the processing for the entire stack of stones, just do it once. And keeping that around as we go through this loop does massive speed ups, because we're doing the calculation for literally billions of stones. So by skipping a whole bunch of calculation, which, one of the primary ways to make programs fast is to not do things, and storing those values around and then doing much smaller cost math, then we get a faster result. So that's it for today. Hope you enjoyed me trying to optimize today. I had a feeling it was dynamic programming, but that also means that it's a good example for maybe how to look at things and how to optimize them. I am happy with how we were able to update the runtime for part 1 and get it down and down and down. It was not going to be fast enough ever taking that approach. So we had to switch it up for part 2 and do the caching approach, but I'm still happy we did both. I hope you enjoyed it. I hope you found it informational, and I will see you tomorrow for day 12.